computer. Awesome, basics of lean. So I think a good example is to try to formalize a very famous Koch book called Software Foundations. So what we're gonna do, we're gonna try to define the natural numbers from scratch. So at the same time, I will display how I use Lean with Copilot and other tools that usually help me. I usually develop Lean with the MATLAB documentation. This is pretty useful. I really like the Google site search, not only searching in the documentation itself. I have Lean Tactic Reference Manual is pretty good. Oh, this is from a class actually, from a class in Northeastern, I think. I like this reference. Let's see, just to see all my sources. Yes, these are official Lean ones. This is tactics by by the developers of Lean, the creators of Lean. Functional programming in Lean, the manual. Let's see. Yeah, these three are pretty useful. And I don't have it there, but Moogle is pretty useful for finding theorems. So these are like my basic things that I usually have for Lean.
Okay.
Copilot, I usually have it on. So yes, let's see if it can define natural numbers for us. Or actually, I'll just do it from my head. So in Lean, you have you create data types. So you create something called inductive data types. So let's call it my net, or I usually like to call it Unary net. Where it's going to be a type. So Unary net is a type. This is why it has type, and it's already defining us things for us. So you define constructors. It helps us construct data. So 0, and it's basically sort of a function that maps to data. This one will just return a unary net. It's just a constant function. You can think of it like 0, like this, and it creates just that object, like that string, like that serialization. Successor function takes in another net and returns a net. So for example, suc 0 is basically an object. It represents the number 1. If you want to do 2, you can do like this. This conceptually is 1, this conceptually is 2, etc. Does this sort of make sense?
Yes. Yes.
Awesome. So now let's try to use
Now,
it.
the inductive declaration, what is that doing? It's just I mean, I want to understand what it is.
Yes, okay, yeah. So inductive is a keyword in Lean that defines you can think of it sort of like a data type, like a class, some sort of like data. Usually when you tell Lean, I'm creating a data type, it will let you create now objects of that data type. By telling it that it's inductive, you're telling it basically that it's recursive, self-referencing. This is why here it's self-referencing already. You have a successor function, and it takes in a NAT, and it returns another NAT. So that is part of the inductive part of it. The other thing, Lean is a little bit new to me, but I know that Coq does something like this, and I know Lean does it too. But when you create an inductive type, Lean automatically will create something called induction theorems and other types of like useful data, like not metadata, but like auxiliary data that type of object always has. So for example, what does it mean that it creates inductive theorems? In this case, we're creating 0 and 1, right? And 2 and whatever.
Yes.
Um, Usually in mathematics, you want to prove some statement P for all n. So you want to show that for all n, say of that is a unary net, like some statement P holds. P can just be anything. P can be, I don't know, P can just be that n is greater than 0, which is, I guess, sort of like easy, but we'll do like some sort of real theorem. The point is that this is some statement, and induction will create a theorem so that you can prove theorems of this form. And we will go through an example right now so that you know what that this
Sure,
what
sure,
this
yeah, makes sense.
yes. So let's see. First we want to just do like some sort of simple debugging that this is working. There's something called deriving. I forget what it is. I'm just gonna cheat. Okay, yeah. Repr is like a way to print things, right? Um, so I sort of cheated because I've done this example a little bit before. But the reason is that if I want to evaluate and I want to let's say we don't have this. I want to do 0 unknown identifier. Yes. Unary unary net dot 0. Does that work? Failed to synthesize this instruction on how to display the resulting. Recall that any type implementing the Repr class also implements the lean.eval class. Is
You
it?
have to,
I think
yeah,
it just wants me to do this. Okay, so now it printed this basically. We're asking
yeah,
it to evaluate it. Um, now did it do something? Okay,
space, yeah,
so now it creates the number 2 for us. And this is like a basic debugging statement in the sense that it outputs what we expect, right? Usually check is also useful. You can check the type. So we know that unary nat 0 should be a function of type just unary nat, right? Did I do something wrong? Okay, here it is. Yes, it is what we expect. This one should be also, oh, eval should be of type unary net to unary net, right? This is what we expect. Check,
wait, check,
check, check, sorry. Yes, there we go. And then perfect. Unary successor takes in, okay, this displayed it differently. It takes in some sort of variable called a cross of type unary net and returns unary net. That is what this arrow means, right? It's a function that takes in a constructor function. It's a special type of function that takes in a unary net and returns a unary net.
yeah,
Questions? Does this sort of make sense?
yes.
Awesome. Awesome.
So the eval is not is showing the I mean these statements are just to check, right? So
Yes.
basically you see, okay, okay.
Yeah. They're just to sort of like create this. I wonder, let's do some sort of let's see, um, create, let's create a variable that holds a unary 0. Let's see if it, okay, so this created something. Yeah, cool. So it's a unary 0. Now it's like our variable of type unary net, and it holds the value 0.
Yeah,
And it tells us exactly what we expected. It is this little guy, right? It is unary 0. So at some point, it can be like a little annoying to have to write unary net. So I'm just gonna say open. But I guess like maybe you forget the syntax. What you can say is like write a well, I guess I'm cheating because I know open is, but how do I stop referencing the name UnaryNet everywhere? Yes, that's exactly true. Let's see if it, okay, there you go. Eventually it told us the So things like this you can do to have open what do you call it? Copilot help you. So now I can do exactly the same example, but now I just do 0 this time. And look, it tells us Unary nat. Cool. Well, that saves time, basically. Right?
Yeah.
Excellent. Okay, awesome. Let's see. I told you about this creating induction for us. Let's see if I can force GP like Copilot show it to me. Show me the induction theorem. Or there you go. Oh, there, look, there you go. Amazing. It does do it. This might be a little bit. I don't actually know what this. I mean, I know what it should mean. I don't know. I would have to think through it. Let me think about it. Okay, so it's defining, I think, some sort of function of this type. Unary need to sort you. Yeah, I think this might be like too much to go into it, but for like our first time we do lean, but that's what induction does. Induction creates a variable and it creates auxiliary theorems for that type of data. And we'll use, and I'll explain it. I'll explain what induction is today, but I think it's easier to do it hands-on with a real proof than like abstractly.
Okay.
Any questions? I think I'll move on. So the first thing we need to do is define addition. So let's try to do it without Copilot. Let's see if Brenda remembers. So define add, oh, def, sorry. I started writing Python by accident. Def add. Let's do unary, or let's do add left. I don't know. Actually, maybe should I cheat real quick? So I don't know. Maybe it'll turn off. Okay, it doesn't matter. I'm just gonna do add left. Add left. And we're gonna define a unary function. We're gonna do a function that so yeah, I guess there's different syntax for this. I'll show you the first one. This one is
Okay.
this one this one means that you have a unary, you have a function called add left. It takes in two variables that we are not naming, and it returns a unary net, right?
Okay.
When the first argument is 0 and the second argument is just a net, look, it even tells you if you hover your mouse, it's a net, you just return a unary net. When the first one is not 0, it means that we need to recurse, right?
Yeah.
Right? So what you do is you open up the onion layer of successor. So you get the successor function and put it in front, and then you keep adding. Oop. Does that sort of make sense why this is the way is defined?
Yeah.
Yeah. So that is one way to define add left, and they call it because we're recursing on the left. Oh, look, it's already trying to define add right for me. For the sake of learning lean, I'm just going to define. Yeah, so it does let you do this. I think this would be super illegal in nearly any other language, right? Like a prime.
So that's the next value.
No, this is like I'm defining a new function called add left prime.
Oh, okay.
So this
Okay.
is like add left 2. But
Yes.
but
Yes.
because we're doing a language that for mathematicians and they like the notation prime, we're using prime. And you can keep adding primes. Yeah, it's just like in the grammar of lean, basically.
Yeah. Yeah.
So now the reason I'm defining it again is that I'm gonna try to define it like a little bit more traditional. Um, Oopsie. Let's see. A B C D F G J K A B C M N. Okay, great. It did do it, right? Okay, this is like a functional programming language way to do it, right? This is exactly
So
these two are the same. I don't know which one's syntactic sugar for which one, but we're saying match M. And once we match M, it will be either 0 or successor, right? I'm gonna yeah, we had to do the M prime this time because we're actually explicitly naming the variables. So it just recursively adds. Yeah, so that is it, basically. Does this make sense?
Yeah,
Yeah.
yeah, 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 it
Um,
does.
I'm gonna comment it out, but there we go. The reason this one's I don't know if this is true, but I'm gonna make it up. I think this one's preferred. Maybe that's why Copilot
Okay.
suggested that first, because even though this is because it looks more like math. It's like a rewrite rule. It's an equation nearly, right? When you have 0 plus n equals n, right? This is basically what this means. This is 0 plus n equals n. It really looks like an equation, right? A rewrite rule. Yeah, this is what this means, right?
Yeah. I mean, what I think that what's weird is how it defines the arguments to the function, right? I mean, so the unary, basically takes two unary.
Oh, sorry, say I can't hear you for a second. Try again.
Like it because it's more math-like than the one before. I mean, the one below, it's more like, like a programming language kind of function definition, right?
Yeah.
And what I was saying about how you define the arguments to the function in the first case, where you have the arrow, so you have the three, the one above, yeah, right in the definition above the first line, add left, and then it defines, the three unary nats, right? So one is the return value, and the other two are the arguments.
Yes. Correct. This is the argument, and this is the return value.
Yeah, no. If you go to the line above, yes, that. So that definition of those three unary nats in a row,
Yeah.
it's kind of like I don't know. To me, it's more natural to define it, as a function. But anyways,
This is a function.
yes, no, I know it is. It's just how it defines the arguments and return value.
Yes. I don't know if this helps. Let me just show you.
It does help. I understand it. It's not that I don't understand. I was just commenting on the fact that to me it's clearer to have the definition of the function more of like a programming language kind, which is
Uh-huh.
the option below,
Uh-huh.
than the one above. But it's okay. I understand.
Yeah, yeah. No, if it helps, um, this looks, yeah. Well, I don't know. If you remember, Glean is like a theorem proving language. So this is
Yeah,
type is like the theorem. So this is like the theorem for the theorem. This is the theorem for called add left, and this is the program or the proof because of the
yeah,
Howard correspondence. But I'm curious. I wonder if we can do this. Let's see if Lean allows us to do something in between. I'm not sure if it will, but let's see. See if it lets us do it. It doesn't like it. Sad.
yeah, yeah,
Maybe we do this. No, it doesn't. Okay, this is like it does not like this. Okay, but we
yeah,
tried. We try. I understand why from a software development it's not. It's I mean naming variables is nice.
yeah. Yeah, no, it's and it has its own notation, right? So
Yeah. So let's play with this real quick.
yeah,
Um, I think eval add left 0 0 should return 0, right? Here it is.
yes,
Add left 0 successor 0 should return successor 0, I think. Yay, it does do it. And add left successor let's do something. Okay. I think this should be again the same. And what about okay, this should be successor 0.
yeah,
Perfect. And let's just do check the type of add left. It should be nat to nat to,
Unary net.
yeah, unary nat to unary nat to unary nat. And that's, I guess that is true. There we go. It's unary net to unary net, but it
Yeah.
automatically created a rather ugly name, I guess. And then check, we can do partial function applications too. So you can do 0, and this should be unary net to unary net, right?
Yes.
Which I think is sort of cool. Add left. Okay, well, if you apply the final one, it actually just works, I guess, right?
Yeah.
Yeah, it should be a function that returns unary net, and it is. I mean, it's just
Yes.
it's just like the constant function. Cool. So that is that.
Yeah.
You can also, let's see, you can also write a theorem, I think. You can write a theorem, add left. So let's do 0 plus 0. And let's just show that for any natural number. Oops, sorry. Copilot went crazy. I didn't want it to do that. Unary nat. Sometimes it's annoying because I just wanted to like give me the next part, but it just gives me all of it.
Yeah.
Or
Yeah.
for all n, we just want to show one of these examples basically manually. So we want to do like as a theorem, add left. No, yeah, I don't know. That probably won't work. So add 0, 0 equals 0, right? Oh,
Mm-hmm.
0. That makes, that's the theorem we want to do, right?
Yes.
So so remember that theorems are types in Lean. This is the theorem we want to prove. So for any natural number, 0 plus 0 equals 0.
Yeah.
On the right hand, we're defining, if you remember here, actually, I'm gonna write it below as a reminder. This notation sort of defines what the program needs to be on the right, or the proof term, right? So the proof
Yes.
term for this theorem is, we just need to do it. So one way to do it is to write the theorem, like the program directly. So it's, would it be, I don't, so what the most standard way to do a theorem like this is to go into tactic mode. That's what it means to say the word by. So by puts it into tactic mode. Tactics are just functions that manipulate the proof state or the theorem you're trying to complete. And in this case, we have for all n. And if you imagine this being like a theorem in math, it's basically, it's like, let's write it as a comment. It's just for all n of type unary nat. I'm just gonna write nat. N plus 0, 0 plus 0 equals 0, right? That is what,
Yeah.
that is the theorem. Um, let's see. Boop, 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 boop. What am I trying to do? Okay, yeah. So this is the theorem. If you were to do the proof, you would say something like, consider some n. Consider some natural number n. Okay. And then that would sort of like invoke n, basically.
Mm-hmm.
Well, I guess because there's no arguments, this theorem is
Yes.
sort of silly, but let's just put it here. Let's do okay, no, it's fine. Let's do a simple proof. This is fine. This is a fine theorem to do. So consider some natural numbers. That removes this part, and then we just need to show that this is true. Okay, so 0 plus 0 is 0 because of our definition of addition, add left. And that completes the proof, basically. That's it. That's what we want to translate into Lean. So the first thing we do is that we have the theorem here in the proof state. And we are in a tactic state, and we want to show our goal. for all natural numbers, it is, hold on, unresolved goal. Yes. Sorry. Okay. Yeah, that just like accepts the proof.
Okay.
Yeah, I think Lean did some simplifications for us. I think I'm just gonna change the proof because maybe this is like too simple. I wonder if that's why it looks weird. Consider some natural number n. We want to prove that 0 plus n equals n. So it is what we want because I'm just looking at our definition right here to write the theorem we want. I want to, okay. Okay, so cool. This looks like a little bit more sensible.
Okay.
We have for all natural, or for all unary natural numbers, we want to show that add left is equal to n.
Yes.
So first we introduce n into, we could say, consider some n.
Mm-hmm.
And then we basically tell it to use this rewrite rule, right?
Yeah.
So we instruct Lean to use that rewrite rule. Ta-da! And that's it. It did it. No goals. It closed the proof. It works now. That's it.
Okay.
That's the entire proof. Does this
That
sort
is
of,
the proof.
that is the proof. I think that proof.
So the tactic is what's proving it.
No. Yes and no. Um, when you define this theorem with this type, and when you go into tactic mode, you start
Mhm.
proving the theorem, or under the hood, Lean starts building the proof term. The first thing it does is it introduces n.
Yeah.
That's it. That's the first step.
Yeah.
The tactics only manipulate the goal locally. That's why they're called tactics and not strategies. Then here, the only real thing we can do that it looks sensible is to use the rewrite rule to rewrite the left side. I think, yeah, okay. Oh, actually, yes. Okay, here, this is actually nice. So we have the rewrite rule, and I tell it to use this definition. And if I put my cursor right there, it rewrites the left side. Did you see it?
Can you do it again?
Yeah. So if we're here, before it rewrites, we have add left 0 n, right? This is the expression that we have.
Okay.
But if I put my cursor here, now it rewrote it. Do you see it?
Yes. Yes.
And then the rewrite rule implicitly will just unify the left and the right. Basically, it will on its own, it's going to notice that they're the same and close the proof after you leave the tactic. And that's the next click here.
Okay.
And that's it.
That's the proof.
That's the proof. That's the proof. Yeah, I think to one variation, I wonder if this works. I wonder what this does. Okay, this only does the rewrite. It doesn't actually close the proof. So rewrite out automatically like detected that both sides were the same, right?
Yes.
So I wonder, here we need to say refl, and then it closes the proof. That
Stands for what?
for reflexivity. Reflexivity just means check that the left and the right are the same.
Okay.
So actually, if you put your mouse on anything, VS Code, it will tell you what it is. Refl tries to prove the current goal using reflexivity. This is supposed to be an extensible tactic, and users can add their own support and for new reflexive relations. Makes sense because as you can see, we can define anything from scratch. So maybe you need to define your own refl like your own relations. Yeah, so unfold is another tactic. It actually explains what it is there, but you could see what it does. It just rewrote the it unfolded the definition. That's what this means. It unfolded this definition using our definition up here.
Yeah.
Yeah, I think the standard way would be to honestly, this was a little bit more manual that most people would write the proof. This is like more standard.
Okay.
I wonder if that's even too much. I wonder if simp would have worked. Okay, no, it didn't work. Simp is like a simplification tactic. It just tries to apply tactics and lemmas on its own until it works. Actually, that's the way I think of it, but obviously that model is incomplete. This is exactly what it's doing. Um, I mean, it's hard to remember all that. So instead, I think simp left, does that work? Let's see. If I put my cursor here, does it? Oh, it already does it.
Yeah.
It does it all. It doesn't matter where I put the cursor. Interesting. Um, hey, I don't know if I've shown you this trick. Rewrite question mark. Unknown tactic. Oh, I don't remember how to do that, but I'll Google that later. But anyway, let's just leave this one because this is the more standard proof. Any question?
So here we knew what definition to apply to this tactic, right?
Yes, that is true.
So you need to know for a given theorem what definitions you can apply.
Yes, yes, that is very different. We'll try to do a theorem, a proof that is a little bit more serious in the bit, so that
Okay.
you see. Yes, exactly. That is actually why I opened up Moogle. Moogle helps you find theorems. So if you want to do like, what theorem did we use? Add left, add natural numbers. It will show you like all the theorems about natural numbers. Yeah, there's yeah, look, there it is.
Yeah.
Um, you can also go to the lean library. I think it jumps you to it. Yeah, look at this. Yeah,
Okay. Okay.
yeah.
So all those links that you have are very useful.
Right, right. Yeah. I wonder if this one does it too, the documentation. What did we Google? Add natural number. Mm,
Oh.
yes, this is why sometimes I don't like this search bar and I like this one. Yeah, this sends you to things that are a little bit easier to see.
Mhm.
Inductive int. Oh, cool. This is interesting. It shows you how they define integers in lean. Yeah, that's cool. Or let's go here. What does this do? Okay, this one looks better. Yeah, okay, this is more or less, I think, what we're trying to do, but this is the full lean way to do it. The point
Yeah.
the point is really not really to I'm just trying to demonstrate different ways to search for theorems because as you see, you can't do anything without finding the right definitions, right?
Yeah.
So this is
Yeah.
so like this might yeah, this is very important. Cool. Awesome. So I'm gonna another question.
No, no, no. Go ahead.
Yeah. So this is like sort of non-human. There's no plus sign, right? So I'm gonna try to add the plus sign notation. So define add left with infix notation. There we go. Okay, it decided to do two pluses, but we can do the same theorem. But now, okay, yeah, it's mad because there's two theorems called the same way. And now we have plus, oh, plus. And now, look, there's a plus there. Did you see that, Gil?
Yeah. Yeah.
Here, there's a plus there. And I can put spaces, maybe? I wonder if that makes the theorem a little bit nicer. Oh, look, it put space now.
Okay. Okay.
Oh, I think yeah, there's a space now. You can do space L if you want to emphasize that it's an add left, I guess. Oh, but there's, of course, yeah. Now it's mad at me. Let's see. Yeah, but maybe that L is just like confusing. But I just wanted to show you you could do it if you wanted.
Okay.
I wonder if you
Okay.
could like underscore. Oh, it doesn't let me. Okay, it doesn't let
Well,
me.
this is part of the language, right? But what does it infix L colon 65 mean?
Yeah, so infix is this notation. Like it basically it's just infix is the so when you have binary operations like this one, this is a binary operation. It's adding something on the left and something on the right.
Mm-hmm.
Instead, infix changes it to have the operator in the center, and I renamed
Okay.
it E plus.
And the 65?
Yes, that is a good question. What does 65 mean? Okay. Um, the details, I guess like if I look them up, I can remember them. But
Uh, uh,
the high level idea is that when you have something like this, Lean doesn't know, like we know that that it should bind like this, right? So basically, the 65 tells it the precedence. This is like a syntax. This is like a tree. How do you draw a tree here? So we have A plus B plus. We have this expression, but Lean doesn't know if it should do like if it should do this.
yeah.
Oh, sorry. How do I undo things? Oh no, I don't know how to use this. Oh, okay, here it is. Um, okay. Plus. No, no plus. Plus
Yeah.
times B C if we mean this or if we mean any other thing, right? If we mean
Yes.
C here plus a B. Oops, I forgot the little arrows. So you need to tell it which bind more strongly, which have precedence.
Okay.
That is the right terminology. Um, that just like I'm gonna erase it. That just like
It's
the 65 somehow specifies the precedence, basically.
okay. Okay, of
If
that
we have
operator.
yeah, if we have different functions fighting for precedence, um, this will tell it who wins, basically. So that we would define like multiplication with its own, let's see, define multiplication with infix notation and put precedence. Okay, first it needs to define.
The multiplication.
Yeah, but it doesn't. Yeah, I don't know if this definition is right, but I'm just sort of, I just want to see the infix
The
note.
infix.
Yeah. Okay, 70. Okay, yeah. It seems that maybe that means it has a higher precedence. So I'll just compare
Okay.
the integer and choose which one to bind more strongly. So bind more
I
strongly,
see.
which one to put the parentheses around. So which
Yeah.
one to put at the bottom of the tree. I'm going to delete this because this is probably wrong. I just blindly let Copilot do it.
Yeah.
Cool. Does that help?
Yes.
Yeah. Since we won't, I don't think we will do multiplication. I won't go into it, but let's see. Okay, now, okay, we did, okay, fine, cool. So finally, we have 0 plus n. Um, and we're gonna now do finally a theorem that is a little bit more serious, not super serious, but it's gonna be, it requires induction now.
Okay.
Plus 0 for all. So we're gonna just basically do, oh, it did it in one go. I'm just gonna stop it. Um, for all n plus 0 equals n.
Mm-hmm.
Oh, this is our theorem. So what do you think we should do first?
Well, you need to introduce
introduce n, right?
And yeah,
So now we have, this does consider some n of type
yes.
nat, unary nat. Cool, we did progress. Okay, so now what?
You have the definition, right?
Yes, we
Or
have
not?
in here. Yes.
Yeah, yeah. So we do a rewrite of the definition again, right?
Okay, let's try it. Um,
Okay, didn't like it.
it has, so the reason it does, why doesn't this work? Why do you think it doesn't work, Gil? I can
Hmm.
tell you, but I'll let you suffer through it a little bit.
Why doesn't it work? Um, Speaks of the order of the um of the terms.
Yes, it is.
Zero has to be first because because of the way it's defined. Because any number is a successor of zero, right?
Yeah. Yes. So that is part of the issue. The orders are wrong. Okay, if that's true, then why don't we just use the second definition, right? Like whatever. Let's use the second one. If the first one doesn't work, use the second one. Rewrite should do that automatically, but it didn't. It failed. Why did it fail?
Because it's not specified for zero, right? I mean, it's specifying successor, right?
Yes, exactly. Yes, that's
So
why.
you need to have an add right function.
That is not a bad idea. Um,
Or have another rule in there, right?
yes, that could work. I'll tell you what we use, what quote unquote the right way to do it is. The right way to do it is to use induction, basically.
Okay.
And the question is like, why do we want to do induction? Okay, I'll show you what induction does. So induction in mathematics and programming languages, actually, this is a programming languages concept too, very important, is that if you have a constructor, if you have a data type of with constructors, you automatically get, if you want, usually what you want to show is that some property holds for all data types. So like I said, right, you want to show that some property P, this case, this property, actually this property, just this property. In this case, the property that we're considering is this one. You want to show that it holds for all n. So you want to show for all n, you want to show this. So to show that, one way to do it is intuitively think about it. If some property holds for all natural numbers, it means that it should hold for in any possible way you construct that natural number, it should hold. It doesn't matter how you construct it, it should hold recursively. So what that means is it should hold for the base case. It should hold for this case, for zero. P of zero should hold, right?
Yes.
Okay, if we want to show that it holds for any, then it should hold for when we build things with successor, right?
Yes.
So if we have this property hold, assuming that it holds for some, for a smaller one, say that it already holds for this smaller n prime, I called it, then you should be able to show that it holds for n prime. If it holds for this little n, then it should hold for the next one,
Yes.
right? Basically, this is a loop.
Yeah.
This is like
Yes.
a deep mathematical thing. Induction and loops and recursion are related.
Yep.
So basically, if you start off by the property holding for zero, you basically first show that. And that is like and then if you show this arrow, it will hold for all of them. So this, if you have those two, you have P of n. Does that sort of make sense? In a
I
way,
mean, it makes sense, but I mean, I don't know how you represent this, right?
No, yes,
So
but does it make I'll show you in a second, but does this make intuitive sense? Like
it
first,
does.
if you have it true for the first natural number, and you have it, and you can build any natural number from another one with that property, then you can construct it for all of them.
Yes.
I think that should be some sort of theory. Like this is called induction, and I'm gonna write pseudo-lean, and it should be something like this: unary nat dot induct equal, and the theorem should be something like, oh look, it already wrote it for me. For all zeros, for the base case, and for any way to construct a natural number from a previous one, if you have all of this, if this is true, then you get that you can construct it for all of them.
Yes.
So I wonder if we can, let's see, check. I wonder if this is actually in induct. Is this like, so because lean is a little new to me. Okay, let's just see, like this thing actually exists in lean when we define induction up here. So I'm just gonna try to force it to show me it, to show me the induction theorem. Show me the induction principle for unary. Okay. Okay, it did rec. We remember we did this. So this must be it. Is there like a different one? Because I can't understand what this means. Oh, print. It did print. Check. Yeah, let's do check. Okay, 0.
You see.
Successor. Look, it even highlights it for us, I think. Oh, I can't quite. I think if I spent some time, I could figure it out, but I don't want to spend it right now. The point is that it does. The point is that it exists. It's probably this guy, but this theorem exists. Luckily, this is sort of like internals of lean. You don't really need to know how to do proofs. What we need is our proof to work here. We have n, and there's two ways to build n's. With 0 and successors, and that's all we're gonna tell lean to do. We're gonna do induction on n. Okay, let's see. Induction with sorry, I forget. Okay, I'm just gonna tell it in natural language because I can't remember the syntax, but I can cheat in a second if I forget. Do induction on n and call the induction hypothesis. Okay, induction hypothesis IH. Okay, let's see if that. Okay, it's not doing it.
You have a typo on the do on the natural language. I don't know if that's
Which one? Sorry. Where?
right in the line above induction. It's a typo, so I don't know if that affects
This
what you're
one?
getting. No, the line above.
Here?
No, the natural language one, the green, where it
Uh,
says do induction.
oh,
You
but this is a comment.
It's just a comment. It's not going to be taken
No,
into account. Okay,
no,
okay, okay,
this is a comment for Copilot to help me write the syntax.
okay.
I'm-
So if the typo doesn't really matter for Copilot.
Well, this is not a typo. This is a comment.
I understand that, but induction is not spelled correctly, so I don't know if that
Oh, I
affects.
see. Yeah, I see what you mean. Now it's in. Now
I
it
mean,
is.
I don't know if that, I mean, Copilot might be smart enough to figure that out, right?
Yeah. Well, what about now?
Yeah, right now it's I mean it's correct, but I don't know if you're gonna get what you need
Yeah, me
from
neither.
Copilot.
Yeah, it didn't. So I'm just gonna cheat real quick. Um, induction and with IC. Cool. Let's do that. Okay. Okay, so there's when we have induction, we have basically two cases, right? We have one. So n can be we have two cases when n is 0 or when n is constructed from a successor, right?
Yes.
So there's two cases, 0 and successor of n. There's two in constructor.
Mhm.
So we're gonna try to do this one, and we're gonna try to do the proof for 0. See, it already only focused on 0 for us, right? It wrote the theorem we want. Do you see?
Yeah.
Okay, so I think this should work with rewrite. No, has not been provided. Why didn't it work? Okay, would simp work? Simp made no progress. I'm a little bit puzzled why. Okay. 0
Doesn't.
and so 0 n should return 0. It's not liking it. Okay, hold on. Let me see. Oh, okay. That did do it. Okay, there it is. 0 equals 0. No goals. Perfect. That worked.
Okay.
Successor. Okay, successor. Okay. Okay, yeah, okay. The second case is the inductive hypothesis, right? So in the inductive case, so in the first case, we need to show, so induction works like this. You need to show P holds for 0, and you need to show that it works for all the constructors, basically. The first constructor is just as constant. The second one is successor. So we just showed it for P of 0, which is, the proof is pretty simple. It's 0 plus 0 is true by add left. When we need to figure out what the proof is, we would have to figure it out, which is why we're doing it. And the first thing is that to prove this, we basically have to show that we can construct a natural number, Sn prime, with the property we want, if we assume this is true. So we're assuming it. That is called the inductive hypothesis. So we're basically assuming, I'm calling it IH. I'm calling it, so the inductive hypothesis is this guy.
Yeah.
So we have this, and we look at our proof, and intuitively we can see that if we could just move this constructor outside and put n prime plus 0, like on its own. Right now, if we switch the brackets, basically, just here, we could apply the induction hypothesis, make it n prime, and then have the left and right be the same, right? Do you see that?
Not quite. I'm a little bit lost here.
Okay,
So.
let me say it again. Look at the proof we have on the, or like the proof state we have. It's, I'm gonna put brackets to make it clear. Suck n prime. Okay, the thing is that it's not showing it anymore, which is sort of annoying. I'm just gonna try to write it here. This is we want to show. We want to show this, right? Right? Does this make sense? This is what we want to show. However, this is what we want to show. We want to show this, sorry. We want to show, well, this is our proof state, actually. Sorry. This is our proof state. And we want to show this. This is what we want to show. This is our proof state.
Yes.
So if you notice, if we just put the bracket here, this simplifies to n prime.
Yes.
And now it's the same as the right.
It is. Yes.
Okay. So the question is, how do we force Lean to do that? And the issue is that if you look at it right now, that's not the way it is, because successor binds to n prime.
Yes.
Look, it even highlights it for us. You see it? I put my cursor under successor and it only colors all the way here.
Yes. Yes.
So plus, remember, plus is just a function that we pre-printed, right? With this infix notation. So if I
Yes.
put my thingy there, it tells me the entire all the arguments to it. You can do
I
that.
see.
You can do that here too. And I think you can do that here. Okay, you can't, but whatever. You can do it here. Equality is also, look, it even tells you what the function is. You see it?
Yes.
So lean is magical. You can just put your cursor anywhere and it tells you everything about it. Or something about it. Actually, you can jump to it, I think. There was a way to jump. Oh, cool, look. So if you are debugging things, okay. I just want to show you a quick trick. If you put your cursor somewhere
Mm-hmm.
and you hover over it and you do, at least in my Mac, for you it's probably control, but for me it's command click, it
Mm-hmm.
jumps to the definition. And that is very useful because if you're doing a real proof that isn't like, we just wrote this function, so we remember it. But if like a month later, you don't know what the hell that is, you know, you,
Yeah.
you can jump to it. And especially if it's like something in the standard library, it'll jump into it in mathlib and you can see the definition.
I see.
Yeah, does that sort of make sense, Gil?
Yeah. Yeah.
Yeah, so right here, we're just going to try to switch the brackets around so that we can actually
Okay.
why. So the thing is that by putting so if I put the brackets, the issue is that this statement is exactly the statement we want to prove, you know?
Yes.
So
Yes.
how do we, so this is where induction is quote unquote magical, is that because we did the base case, we are
Mm-hmm.
allowed to pretend that our theorem is true.
I mean, we have to prove for successor. So, I mean, we have to prove for +1, right? Or
Yes,
or
yes.
or, or
We have to show it that it's true for one, but we get P of n for free.
okay.
After does that make sense? That's like an important
Wait,
consideration.
we get it for free because of the first statement.
Yes.
Okay, because of add left, because we are doing the rewrite of add left.
No, no, no. We get it for free because we proved that 0 plus 0 equals 0.
Yes.
Okay, I'm lying a little bit, but I'll explain it in more depth
No,
fully.
no, I get it. I understand. Okay.
But when you do induction, it gives you the theorem you want to prove for free.
I see.
So,
Okay.
so that is what induction, the tactic induction does that is magical. It will give you the induction hypothesis, which is the theorem you're trying to prove for free, basically.
Yeah. Okay.
And the reason it's like a plausible thing to be doing is because you should have already proved it for your base case. Right?
Yes.
It's sort of like a for loop. If your first value isn't correct, I mean, you can write the for loop and you can compute the next value correctly, and it will compute that loop will be correct. But if your first value isn't right, you don't get to prove the top theorem.
Yeah.
So
Yeah.
like you can prove this one without proving this one, but you will never prove your top theorem, basically.
Yeah, I see.
Yeah, so that's the trick. The trick is to figure out how to, in this proof at least, how to change the brackets such that we can invoke the induction hypothesis and complete our proof.
Okay.
I don't know how to do it, so let's try it. Let's see if I can do it. So
Okay.
let's just think about it. So we have a successor, and okay, what I would do is the plus. Let's see, I would try to use the definition of plus to move the successor outside, which is exactly what this is.
Yes.
So let's just do that. Let's see if it lets me do it. Oh no, okay, that's too much. Okay. Okay. Or actually it's fine. Or I don't know. I feel like that's too much, but okay. Rewrite. Look, do you see it?
Well, okay. Yeah, I see
So
it.
so before it, it's like this. After it, there's a bracket here. Do you see that?
So that's what induction is doing.
No,
So
well,
it's
no, induction. There's no induction yet. We just did the rewrite using our definition of addition left.
yes. No, that I understand. So what I'm saying is that it's adding the brackets because it's doing the rewrite, but it's because we're using this induction I mean I don't know this induction hypothesis.
Yes. Yeah. No. There's no induction hypothesis yet. The induction hypothesis is a fact in our context that we can use later. Right now, the only thing I did was rewrite successor. So the only thing I did is I have this term. I told it rewrite
Yes.
with this function.
Yes.
Rewrite like this. I'm gonna just actually write the notation. Write it like the rewrite it with add left, and that gives us this matches this, right?
Yes.
So we get we just get
Yes.
this basically.
Okay.
So that's all we did. We did not do any induction hypothesis yet. Does that make sense?
Just did a rewrite. Yeah. Yeah.
Just did a rewrite, exactly. Okay, perfect. Does that make sense?
Yes.
Excellent. So now that we have this, we can use this fact as a rewrite. Because they're equal, we can either rewrite n prime to n prime plus 0, or in reverse, we can rewrite n prime plus 0 to n prime. So we can do the rewrite from left to right or right to left, right? So we just need to do another rewrite, right? Rewrite, hypothesis,
Okay.
the induction hypothesis. And because I did, okay, cool. Did you see that? Look.
Yeah.
So we
Yeah.
have
So that rewrite is basically doing the
using the induction hypothesis.
yeah.
And now if you remember from the previous proof, rewrite does REFL on its own.
Yes.
The left and right unify in the sense that this is the same as this is the same as this, so it works.
It's proven. Okay.
Perfect.
All
So
right.
that's a real proof for you, Gil.
Okay.
I'll show you. I think in reality, nobody would have written the proof this way. I think people would have written it like this. Like I would have just done the addition and then
And
in all in one like one call to rewrite.
okay.
I think that's the most likely way people would have done it.
Okay.
I'm curious, just out of an experiment. I wonder if onfold IH does anything. No, it doesn't like it. Okay, I was just curious.
Okay.
What about simp IH? Does this work? Okay, simp works. Okay, sometimes simp works. I was
So
just
simp is what kind of tactic is that?
yes. So rewrite, I think of rewrite like a surgeon, like an incision. Like it's very precise and it does it very carefully what you want it to do.
Yeah.
Simp, I think of it more of like a let's hope it works. Like
I see.
it's like a hammer. Like it will try to do lots of simplifications. Let's see.
Okay. Oh,
Here's
so
the
that's what it stands for. So simplify.
simplify. Yeah. Actually, if you hover over it, the simp tactic uses lemmas and hypothesis to simplify the main goal, target, or non-dependent hypothesis. It has many variants. Yeah,
I see.
I think like this is like an complicated thing. Let's see. Add left. Does it do something? Oh darn. It did something weird. Did you see what it did? I think it removed the successors for us. We have It just removed the successor functions. Oh, I guess that's fine. Okay, now we can just use the induction hypothesis.
Yeah.
Darn. Okay, cool. Well, I didn't know that.
So it did the right thing.
Well, I mean, that's because I also noticed that this was the same as the induction hypothesis. Otherwise, we would have been stuck. Simp will do weird things. You don't know where. Sometimes it can. Well, in this case, it simplified it such that the goal happened to, like, the goal worked out, right?
Yeah.
Um, Actually, I think you can finish the proof by assumption. You don't even need. Yeah, that works too. You don't. So assumption just tells Lean that your goal is in the hypothesis space, like it's in the list of facts. If the assumption is, if your goal is in the assumptions, and you're done, right? So that's another way to finish the proof. So I showed you a bunch of ways to finish the proof now. I'll write them here as comments. I think the rewrite one is like the more pretty one, so I'm just gonna leave it there. But the other ones were simp, add left, induction hypothesis, and simp, add left. Yeah, this one, and assumption. All of these are fine. Cool.
Some assumption is basically assuming the induction hypothesis as the
And
proof.
sort of. I'll tell you, I'll write it here so you understand what it does exactly. Let's just hover over it. So assumption tries to solve the main goal using a hypothesis of compatible type, or else fails.
Okay.
The T term notation, which is a shorthand for show T by assumption, tries to solve the main using hypothesis of compatible type. Okay, yeah. So what that means is that we have a name with this type. So remember, types and theorems are the same in Lean. So we have a theorem, we have some name with this type, and it's here. Like, so this thing, this little tilde, I probably should have said at the beginning, means prove. So this is like some standard notation for theorem proving, which is things on the left of this symbol. I don't know what the name are facts. They're just things we know are true.
Yeah.
You can think of it in two ways. Either they're just assumed true, or they have some program or some proof for them.
Yeah.
In this case, we want to show the right-hand side. We want to show that we can that this is actually true. We want to show that we can construct some object with this type, or a
Yeah.
program with this type, or something like that. You can think of it like that. So in this case, we don't need to construct anything. It's just in the assumptions.
Yes.
So we just tell Lean, look at the assumptions.
Yeah. Yeah.
And that's
I
it.
see. I see. Okay.
That is what that did. Yeah. So let me write all the proofs that we can do for this, for the sake of. I think there's a couple more, but I don't know if writing all of them really matters. I like this one. I think this one's the one I would choose because it's more precise, basically.
The rewrite.
Yeah, I think the rewrite is just, in my
Well,
opinion,
and it's more explicit too, right?
I think it's more precise and explicit and less magic going on. Like, I know exactly what it did. Like with
Yeah.
simp, I'm not 100% sure what its simplification rules are and in which order it's applying them. But if I can do a rewrite rule, I'll try to write my proof like that because personally it's more precise. If I just want to get it done, simp will be fine too. Cool.
Yes.
Let's Awesome. I wanted to see if we can prove maybe one of these. Let's see. Do you want to try one of these with me?
I mean, if you want to go for it, I mean, yeah,
Yeah,
sure.
let's try this one. I don't know. So the goal will be to show commutativity. So right now we define things from scratch so much that that we don't really have um anything basically, right? We know that, for example, facts about the natural numbers, that we have n plus m that is equal to m plus n, right? We know that. but we don't have a
Yes.
theorem for it. We don't have
Yes.
a fact that we can use. So this is the proven cock. I'm not going to use it. I'm just going to try to get to it. So so this is the proven cock, but so you need to prove this first. I think. So we can do two things. We can either just try the proving. So let's do it this way. Let's just try to follow the proven cock the way it is,
Okay.
so that we are guaranteed it works, and then we'll try this one directly and see if we can figure out why it's not working. So that's really what happens usually in real development. You have a proof and you can't prove it. You define a lemma, and a lemma like some helper theorem, and then you prove this one first, and then you do it. If you see this here is like the name of this guy,
Yeah.
and they have a rewrite rule, and they have simp just like us, sort of. It's very
To
similar.
simplify. Yeah.
Yeah, Hawk and lean are very similar. I think I forget the exact differences, but we're gonna do this theorem. Okay, so the ultimate goal is this guy. So because Brando cheated, he knows that he needs this first. So all, for all natural numbers, we want to show, okay, perfect, right? That's it. That is our proof. That is just a statement that we need. This looks, so we have two integers this time. So that seems quite sensible to introduce both of them. Okay, so we have two integers, so we can do induction on two things. So,
So let me ask you. Yeah, I don't quite understand the the theorem line where it says n plus success of m equals the success of n plus m.
yes,
What is it saying?
it's saying that n plus, it's saying this.
Is
Like it
it?
doesn't, yes, successor is that, this is what it's saying.
Yeah, but it says n plus successor m
Yes. So
equals successor n plus m.
yes.
I'm not sure how to map that to n plus m equals n plus m.
So this means, do you agree that n plus successor of m is equal to this?
Yes.
Okay, so if we have two numbers and we add one to them, it's the same as, it doesn't matter where we add the one, right? Where we add one.
Yes.
So that's what this theorem is saying.
Yeah. But I mean it's okay. So I guess that this is a step for us to prove the one below, right?
Yes, right. That's why it's
So
coming.
we're starting on proving it for the plus one case.
So this doesn't, so I am sort of like cheating in the sense that I know this proof requires this fact.
Yes.
So
Yes.
I'm just conjuring it by magic right now.
Yeah. Yeah.
Like in
Yeah.
a real development, it would have showed up, but I'm just gonna go straight. We're gonna do it in reverse. We're gonna do it knowing the answer and then like try it from scratch rather risking being stuck and like not being able to solve it
Yeah. Okay.
because we're in our recording basically. Otherwise, we can just stare at it and try to fix it and solve it basically.
Okay.
So we have this. Does the statement make sense?
Yeah, I mean, to the line above, yes.
Perfect. Okay, perfect. Does it make sense in terms of like functions? Like there's a constructor applied to M, and there's a function applied to two natural numbers, and a
Yeah.
constructor applied to the sum of them.
Yes.
Perfect. Everything type checks because plus returns unary net, right?
Yeah.
Successor needs unary net, if you remember. We defined it.
Yes.
So everything type checks. In fact,
Yes.
that's why lean lets us move on. Like if I were to write the, I mean, it's gonna sound silly, but this is not gonna let me write this theorem at all. Like it's like, what the hell are you doing? Yeah, it's
Yes. Yeah.
the type checker doesn't let me do it. Cool. So we have this theorem now. Okay. I don't know what we need to do. And I'm not going to look at the proof in calc. Let's just try to figure it out on our own. Let's see if we can do it. So we have addition. And this is where Brandon will split the screen so that we can look at the addition definition we have. And this is the theorem we want to prove. Let's see. So we have a couple of options, I think. Okay, I wonder if we can. Okay, I see. We can't really. So this doesn't unify with anything in our in our definition, right? I think because the left side is n, but our addition requires successor of m, right?
Yes.
So my first attempt would be to do induction on n so that we can apply that definition and make progress. Does that
Okay.
make sense? That's what I would do. So I would do induction n with 0. Cool. Okay. Raffle, really? Okay. Did it do it? Okay, wow, that was quick. Okay, sorry. I was just curious if it really did that. Okay, so we have our theorem, but now it replaced n with 0
Yeah.
because base case. So now I'm just going to try to simplify this by removing, I think what I would do is just remove all the zeros by using the definition of add left. That should give us the same thing on the left and the right side.
Yeah.
So let's try to add left rewrite. Okay, it only did one of them. Okay. I wonder if what happens if I do that. Okay, it did work.
So you
Okay,
have to do it once per.
per side. Yeah,
Yeah.
yeah. I think
Interesting. Okay.
this is sort of like, I wonder if there must, I try to write it in one line by writing add left twice. Oh, it did work. Okay.
Yeah. Okay.
Oh, okay. Work.
Cool.
Cool. Okay, we did it. Yay.
Yeah. Yeah.
Excellent. Okay, that's so good. Okay. So now we still have to do the top theorem, but now we're going to do it on successor of n, right?
Yes.
Great. So just like last time, we need to name our induction hypothesis and name our variable. Um, right? Let me see. Successor. Yeah, I like that it does that. Successor n prime. Induction hypothesis. Cool. Okay, we have this. I wonder, really, does it do it in one go? Okay, I was just curious if Copilot really knew the answer. It didn't do it.
You have a typo in successor.
Oh, that's maybe why it didn't do it.
Yeah.
Okay, let's give Copilot a shot. Okay, it did something. Okay,
Yeah.
let's not let it do blind things. Let's just look at it for a second. Um, okay, successor is binded here. Okay, so what I would do, let me see.
Oh, that's weird.
The sum is on, I'm just gonna try to move all the successors out. Would that work? Okay, we can only move the ones on the on over here. Okay, so let's not change this guy. Okay, if we change that guy. Okay, we do have a theorem. We proved that n plus 0 equals n. We don't have zeros. Okay, sorry, I'm just sort of thinking out loud a little bit. So this is what it feels to do a real proof, I guess. Okay.
Yes.
So we have this successor. We have this. So this will oh, sorry, this is the thing I don't like sometimes. This will simplify successor M to, it will M in prime. Let's try a couple things. I'm just curious to see. Add left. What does this do? I thought that would happen. I don't like that because, oh, okay. Okay, that's good because we have the induction hypothesis. Do you see it?
Yes.
Okay, great. So now let's use it. Oh, okay. Now it's nearly what we want. I
And
feel.
you have to
Oh, I
rewrite
see.
it.
There's some sort of, yeah, I think the issue is, okay. Do you see the issue?
Well, I'm not sure. You need to simplify.
I think what I would do, okay, okay, hold on. I'm gonna turn back. So we are here, right? Then Brando
Yeah.
noticed that the induction hypotheses can be used to rewrite this, right? So I just went ahead and did it. Yeah, do you see this?
Yeah.
Okay, great, great. So then I noticed, because of the highlighting, that successor is being applied to the return of the plus, right?
Yeah.
So there are a couple things we can do. One, we can use the definition of add left on this side, right? Because this is binded to n prime to make it successor plus n prime plus m, right? And now they're the
Okay.
same. And I think now they're the same, I think.
Oh, I see. I see.
Now they're the same. Well, if they're the same, that's it. I'm
You
done.
proved it.
I proved it.
Okay. Okay.
Um,
I see.
I noticed as I was describing the proof to you right now, I noticed there was
Mm-hmm.
a proof. Um, this is the proof I noticed. Okay, we did this. Now look at this side. This is
Yeah.
the same as this. Oh, okay.
Uh,
Oh, it is this.
no,
Oh no, it isn't. Oh, this is the same.
no,
This is the same
that is the same. Yeah.
as this. Okay, maybe this won't work, but I think it will work just for the sake of showing you a new tactic. This is not going to do what I want, but I think this, um, oh, I think this will do it. Did it do it? No? Oh, I can't remember the syntax. I just wanted to show you. Okay, you can do the rewrites on the left, like in reverse. Anyway, whatever. I couldn't. Anyway, that proof won't work, but
Okay.
well, it won't work. It is a true. Let's see, is it true? Yeah. No, it's not true. This and these are very similar, but not quite the
But
same.
they're not the same.
Yeah, I can apply add left to this, but then at that point we might just finish our proof.
Yes.
Okay, cool. That's it. We're done.
Okay.
Okay,
But we
let's.
haven't proven that. Okay.
We haven't proven this theorem. Okay, let's just name it the same as these guys. Commutativity. Okay. I'm just gonna delete this. Cool. Does this make sense? This is our usual proof.
Mm-hmm.
Um, and we start by doing intros. And actually, I'm gonna do sorry. I want to show you something real quick. I think you will appreciate this. So I'm gonna show you how theorems are indeed programs. So what I'm gonna do is instead of doing intros, I'm gonna define the theorem like this. Now it's the same theorem, but it has no intros
Yeah, because you
because
are defining them. Okay.
as I'm defining them, the theorem is really just. I wonder if the proof will work if I just use def. Yeah, I think they're the same actually. Theorem and def are the same.
Okay.
There's no difference. At least there isn't a difference in Coq, so there wasn't a difference here. And you don't need to rewrite the proof. That is like, this is bad software development, right? Even though it's correct. Because if some detail changes, say add left is renamed or something, then you have to update both proofs, right?
Yeah.
So I'm just gonna do this instead. By I wonder if this works. There we go. Yeah,
Yeah.
it
Yeah.
worked.
Cool. Cool.
Um, one more thing. Let me see. Show me the proof term. Okay, darn it. It didn't do it. Um, in lean 4. Let's see if ChatGPT knows the syntax. Um, yeah, well, let's see. Wonder if Moogle does it better. So right now I'm just sort of trying something. I'm just trying to find it. Um,
Lean metas proof? No, that's not.
I don't know why it's not this. There should just be some command for it. Show me the command in lean 4. Yeah, lean GPT is not very good right now at lean. In fact, it sucks. Yeah. Okay.
Yeah, no, it's not giving you.
But okay, cool, whatever. It's not working. But I'll look this up later. Um, cool, but now you sort of have that feel now.
Yeah.
Awesome. Okay. Okay, let's return to this proof. So we're just going to show that n plus m equals m plus n. Um, well, there isn't. So, okay, so if you notice when we did this proof, I stopped
Mm-hmm.
here and I wanted to apply the definition of add, and I just noticed that I couldn't really simplify the left. So I decided to do induction on n. I could have done induction on m, right? Nothing stops me from doing that. Um,
Okay.
but I chose n, I guessed n because of the structure of my definition, so that I could apply it and move forward, basically.
Okay. Okay.
Here, I'm looking at my statement, and I don't really see a symmetry. They just look symmetrical. N or m look the same to me.
Yeah.
So I don't know. I'm just gonna do n and hope it works. I don't really
Okay.
I don't really have a good reason to try. Luckily, we only have 2 tries, right? There's only 3 things we can do. We can do induction on n, we can do induction on m, or we can do induction on both.
Okay. Yeah.
I'm just gonna try n. So luckily, there's only like a cardinality of 3 to do things here. I'm just gonna do that. Um, cool. Let's just try 0. Let's see what the proof statement is. What happened? Did I do some mistake? Oh, with. Oops. Sorry. Oh, with. Okay, cool. Okay, we have we have both theorems, right? For this. We proved.
Yes.
So let's just Copilot is doing the prime one. Why do we have a prime one? We shouldn't have a prime one.
It's right there. It's the one. Okay.
Oh, okay. I'm just gonna
Um,
remove it because this is not good software development.
yeah.
Oh, to do good software development, we can do this. We can just comment. I really liked our comment here. So I'm just going to, I'm gonna copy it. Oh, sorry. I'm gonna comment this. We can clean it out in a bit. And I'm gonna now use add here. Plus. There we go. We can clean the file in a bit. Or you can have two versions of the files, like the clean one and, you know, the one that we can use for studying. Rewrite. So we just use our both. So I would actually, let's try to not use add left this time. Let's only use like our theorems. So we have 0 plus n equals n and n plus 0 equals n. So we should just be able to use those.
Yeah.
N plus 0. Do it. Yes, it did it.
Okay.
0
Cool.
plus. There we go. Done.
All right.
All right. Yeah, let's. So now we're gonna just do the inductive case. Basically, we're writing the for loop. Okay, so we have this. Okay, now I see why they defined this theorem because of this thing on the right. Like it appears already, right? This thing appears.
Yeah.
Okay, let's just look at it for a second. I'm gonna put my mouse on things to see how things are binded. But of course, they're binded. Of course, successor is binded to n prime, because if it weren't, we would have seen the brackets, right?
Yes.
Cool. Okay. Same for here, but I mean, there's no confusion. There's nothing here. Um, um, mm, sorry, my brain is thinking something else. I just wanted to comment that you can also do X, A, B. This is, I think, called Polish notation. Actually, I guess
Yes.
this is just standard notation. But people call it Polish notation in logic, I think. And there's post, I think it's called prefixed, right? And there's postfixed too. Um, anyway,
Reverse
these are
reverse
just
Polish notation.
yeah, right. Yeah. Does that
Yeah.
exist? I didn't know that term existed.
Well, that's how HP calculators used to work, man.
Oh, nice.
RPN. This is a a thing from the past, a blast from the past.
Well, it still exists. Like Lean uses it. Okay, cool. Let's see. Let's just okay, we have the induction hypothesis. Um, I don't really like applying things randomly, so I'm just gonna try to. So if I move this here and I put brackets here, we have n prime plus n, and then if I revert them, okay, cool, that would work. So if I move the successor here,
Okay.
and then I put and I put a bracket, move it here, put a bracket, move the successor and put a bracket here. That would make them nearly equal. They would just have n prime plus m and m plus n. They would be flipped. So then I can use the induction hypothesis. So that is
Okay.
let's try to do that proof. I don't know
All
if it
right.
will work, but it's better than nothing. I will start on the left because actually I can do exactly what I said using the theorem. Okay, that's why they did this theorem, because they wanted this first step that we required was exactly what I just said, putting successor to the left. That's why the cock people did that.
Yes.
Did you see that?
Yeah. Yeah.
There you go. Woo! Okay, now we can do and we can do add left, right? The reason I knew that is because successor, right? So it's going to use
Yes.
the first case of our addition.
Yeah.
Perfect. Excellent. 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 Okay, now we are nearly done. I'm so
Yes.
tempted to write REFL, but not really, right? We can't really do REFL because we need to do the induction hypothesis. and we're done. Now we are actually done, right? It flipped it.
Oh, I see. Yes. Yes.
So it flipped it because we proved it for the base. Well, I mean,
Yeah.
we had
Yeah.
it as an induction hypothesis, so we just did it.
I mean, it's interesting, and the strategy is pretty interesting, but it's that, I mean, it depended a lot on thinking about defining a theorem for the plus one case so that it can then, be used to prove what we wanted, right?
Right. Yeah.
So there's a lot of intelligence in terms of figuring this stuff out, right?
Right. Right. Yeah, for sure. Yeah. Yeah. I agree. I agree. I think it was it was very interesting.
I mean, it's cool. It's cool. So, I mean, it's pretty interesting.
Let's just finish this with the final proof, and then I think that's enough. I think it's worth trying to do associativity, which is just changing so we already have everything we need, apparently, according to the cock people. So we're just going to finish the final proof by doing um this associativity. So this was commutativity and then associativity,
Mm-hmm.
and then we're done. Okay, Unary net. I think Copilot would have just probably written it for us, but whatever. Like this type of thing is not too hard for Copilot. Okay, excellent. So now the first thing I would do is just intros everything. Cool. Okay. Okay, cool. It's binded on this side. Where is this binded? It's binded on the left. Okay, that's good to know. So this is like at the top of the hierarchy of the syntax tree, right? It's
Okay,
doing plus. Yeah.
yeah, no, I just want to see it. Okay. Yeah.
Right. If we were to draw it, it would be, where's the drawing tool? It would be, oh, that's an eraser. It was P. I'm drawing this.
M plus N.
Yeah, sorry, plus N plus M.
Mm-hmm.
Cool. Okay. Well, I'm just gonna clear it. Clear, 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 clear. No, no clearing. Okay. Um, I'm just gonna erase it manually then. Me not knowing how to use Zoom. Okay. So let's see. We have this. I don't really have any priors. Again, this looks like pretty symmetrical to me just at a first glance. So without any good reason, I'm just gonna try to do induction.
Close N.
Yeah, I don't really know which one I would do. Like, I think maybe the only one I wouldn't recommend to do induction on is like P, because our definition of addition recurses, we defined add left, right? So if we do induction on the first argument of addition, it's probably gonna be give us less problems, right? Because
Yeah.
so I'm never gonna do induction on P on the second one because of the way we defined addition. We could have defined addition on the right, and then all my inductions would have been in the reverse.
And the other way. Yeah. Yeah.
Yeah. So let's just try it. 0. Okay, let's see if the theorem becomes okay. I think we can use our theorem for 0 plus n. N plus 0. I think that should simplify it. It didn't. Oh, sorry. What's going on? Okay, Copilot is being an n plus 0. Sorry. Let me just look at n plus 0. For n 0, okay, it didn't like it. I think it didn't do anything. Um, I wanted to return n plus p. So maybe I'll just gonna do add left. Okay. What about add left again? Okay, perfect. That's it.
Yeah,
Okay, that was an easy proof. It looks sort of
yeah.
weird to have two add lefts in one row, but it worked.
Which we did also in the plus.
Yeah, we did here.
Yeah, actually, yeah, in the one above, yeah, the plus NSM.
I wonder if simp would have been like the thing to be done.
Yeah, that's a good point.
Yeah, okay,
Just
simp.
one. Yeah, simplify applies it.
I mean, this is just like a human thing. Obviously, it had to apply add left twice, no matter what. Simp
Yes,
just did it automatically for us. Like
yes.
there's no benefit. I mean, it's just a little shorter, I guess. Um, we can just say that add left worked too. Cool. Awesome. Ready? Let's do this one. Okay, so our induction hypothesis, as we expect, is associativity, right?
Yes.
So we have we have we have the statement we want to prove. Let's think about what manipulations we can do. I think I'm going to do similar to what I did to the last proof. I'm going to look at which successors I can move around or which additions I can move around. I think in this case, the additions are causing us the problem. So this addition here, okay, this one's like under everything, and it has n plus 0 on this side. Okay, that's the issue. Do you see the issue? Yeah.
Well, I'm sorry, I missed it.
Well, this plus has on the left n plus p and successor n prime.
Hmm.
This plus is like at the bottom of the tree instead of the top,
Yeah.
which makes sense. That is what associativity is about. It's about moving things in the tree and showing they're the same, right?
Yes.
But if you think about it, that is a very non-trivial property of a function. Like you can't really prove that for like general functions don't have that property. Like if you write your like some sort of arbitrary code, obviously that doesn't always hold. You can't just change the arguments that hope it works. So I'm trying to think through what I would do. So we have commutativity. Commutativity switches things around a tree. So that means we can flip m and p. We can flip successor n prime and m plus p. We can flip these two. If we flip these, I don't know if that helps. Um, what I, if we can flip these and we can flip these. Don't, so it seems that the ordering is already correct. Like we have this on the this, then this, then this, this, then this, then this. So let's see. I think maybe the goal should be to remove the successor function somehow so that we can apply the induction hypothesis somewhere. I think right now that's I think the objective because maybe commutativity will become useful later. I don't quite haven't seen forward enough.
Yeah.
So let's try to just remove successors. The only way I think we can do it is by doing, yeah, look at Copilot is already suggesting it. Add left. Okay, it just applied it to the first one. Okay, great. That means we can use the induction hypothesis now. I think we should do add left again so that everything is in terms of, oh, okay, what did it do? Okay, hold on. We have
Just applied it to the first.
it applied it to the first one, but then what if I do add left the second time? Okay. Yes, that makes sense. But does that help us? Don't think that helps us.
Yeah.
Not sure, but I think because it already allows us to do induction hypothesis, I'm gonna apply it. At least I think this is probably a good thing to have. Okay, let's just not try to do it all in one line. I think this is good progress. Okay, now we just need to figure out how to apply the induction hypothesis on the right. I think that's what I would do. So if we just did add left, and what it did was it put it out. It like extracted this successor and it did the summation of n plus m, right?
Yes.
Okay. Does that help us in any way? Can I want to keep pulling this out?
You gotta try.
What is it? Can we do this again? Oh, it just
Oh, what?
right. Well, I mean, add left. Oh wow. Let me see what did it do? Okay,
It
add
just
left. Okay,
it
so
it added P.
yeah, it did it on this one, right?
Yeah.
So
Yeah.
it did prime plus p plus n prime plus m plus p.
Yes.
And then I had
So
already applied the induction hypothesis once. So now it just
yes.
happened to be the same. Cool. And then it's done.
And it is done. Yes.
So the proof wasn't, let's see if we can like rewrite it more thoughtfully, because I sort of did just, honestly, what I did was I know that it requires the induction hypothesis to work. So I just try to apply it once. But honestly, once I got to the second part, I was doing the same strategy. I was just trying to put it in a format to apply it again, but it just happened to
Yes.
be the same already.
Exactly.
Yeah,
You ended up, yeah, you ended up, applying add left correctly so that, you got the right term.
cool. Okay, well I think that's it. We did like some sort of very pretty cool proofs.
Yeah. Yeah. All right.
Awesome. I think I'm gonna stop the recording unless you want to ask some last questions.
No, I think that this is good.
Perfect. Let's stop it then. How do you stop this? Give me 1 second.